Welcome back. So remember, we're now in the part of the course having to do with dynamics beyond diffusion, which is, in some sense, that's most everything or lots of things. And I don't mean to set up diffusion as a straw man, but I do think that it's so important to have an understanding of diffusion because it's so ubiquitous, not only in terms of molecular motions, but in terms of other things that end up becoming diffusion once viewed from the right perspective. And this is one of my points actually in this course about doing physics to it, so to speak, which is that things that are apparently not the same end up being the same. And I don't think I can strongly enough emphasize for you the magic of that and how true that has been so many times in the history of science. And part of the reason that I think that that warning shot across the bow must be heeded is that I feel very confident that that is going to be true in biology over and over and over again. And so we should be on the lookout for it. It should be our instinct to try to find that unity in phenomena and unity in the description of phenomena. So we're using what I will call dynamical systems theory here over and over again as a way to peer into the inner workings of biological systems. So the example that we're going to do first is dynamics of mRNA. And just as a reminder, we're going to unleash this rate equation protocol, and this is perfect. So let me just describe for you the protocol, and then let's do it. So first, we're going to identify the variables of interest. What do we mean by that? Well, in this case, it's pretty straightforward, which is that if we do a fish experiment, we will look at different cells, and each one of them will have a certain number of mRNAs. Let's put aside the question of whether or not experimentally we know how to really properly count mRNAs. Let's assume that that technical challenge has been overcome, and now we know the number of mRNAs per cell. And what I'm going to do is I'm going to look at this population, and I'm going to compute an average. And what I want to do is I want to compute the average as a function of time. So for the moment, we've essentially eliminated the stochasticity. We've eliminated all reference to the fact that different cells have different personalities or different outcomes, to intrinsic and extrinsic noise. We're just going to take the population average. And this is, we should not be too judgmental because, historically, we didn't necessarily have access to the single cell behavior, and so you try to calculate what you can measure. And so in the early days, people could measure the population average, and they could not measure the individual cell quantity of mRNA. So I feel very, very happy to be in that old school mentality for a moment. Okay, the second step in the protocol is to enumerate the ways that those variables can increase or decrease and define the associated rate constants. So in this case, we're going to be thinking about a constitutive promoter, shown here. And this promoter is going to be producing mRNA at a rate R. R has units of number per time. And the mRNAs, there will be M mRNAs, they can also degrade at a rate gamma. So gamma has units of 1 over time as well. And so the dynamics is entirely sort of contained in the fact that the number of mRNAs can increase by virtue of the process described by the rate constant R, and the number of mRNAs can decrease by virtue of the process whose rate is mRNA degradation process, whose rate constant is gamma. Number 3, write down an equation describing the change over each time step delta t. This is really cool, and as you can see, this is something that we've already been doing again and again, and we will continue to do it again and again. And that is amount now is amount before plus the change. In this case, the amount now, the number of mRNAs at time t plus delta t, is given by the number we had before plus, and then I'm going to circle in green, or actually let me underline in green. This is the production term, and this is the degradation term. So we have both production and degradation, and together they give the net rate of increase or decrease of the number of mRNAs. And then step 4 in the protocol is integrate to get an equation describing the time evolution. So we start with a differential equation shown here, and we use it to solve for the time evolution. So that's the concept of our protocol. So now let's actually try and go through it in some little bit more detail. So I just said that m of t plus delta t is equal to m of t, and then plus r delta t, and then minus gamma delta t times m. Now, what's the logic? So this is, let's see here. So this guy is the rate of production, or the probability of producing an mRNA. In the time step delta t. And this thing is, so the gamma delta t is the number of, this is the total thing, is the number of mRNAs degraded in time delta t. So the gamma delta t is the probability of a given mRNA degrading, and then we multiply by m because there's m candidates for this degradation event. Now, as we've done repeatedly, I'm gonna do surgery on this. I'm gonna do my usual thing of subtracting from both sides m of t. I'm gonna divide by delta t. This is shorthand for dm by dt. I'm being sloppy intentionally. I'm not gonna write down things like in the limit that delta t goes to 0 and all that. I'm assuming that you're aware of that is being the basis of how we define the derivative and so on. I'm just going to pass that by, and then this is equal to r minus gamma m. So this is our equation of motion, if you will. This is the dynamical equation, governing equation for the mRNAs, the average number of mRNAs. So I'm going to refer to this as the governing dynamical equation for the number of mRNAs. It tells us, given a knowledge of how many mRNAs there are right now, it tells us how to find the number there are at all subsequent times. Again, in the spirit of the Newtonian moment that I mentioned earlier, or in more sophisticated modern parlance, this is the dynamical systems notion. It's that we start with some initial condition, and given the evolution equation, it tells us how to find all subsequent values of our quantities of interest, which in this case is m. So this equation has an exponential solution, and the way that I guess I would, I'm not going to spend a bunch of time on it, but the way that you might want to think about this is, I don't know. So what might I do? So I have dm by dt is r minus gamma m, and so I can use separation of variables. I just happen to be able to in this case. In general, this is not a very successful way to solve differential equations, but I can rewrite this as dm over r minus gamma m, and that's equal to dt. I will integrate both sides. So let's call this one 1 and this one 2, and we need to tackle each one of these separately. So 1, that's equal to the integral from m0 up to m of t of dm r minus gamma m. Let me add a page here. Switch back to blue. So let's call z equals r minus gamma m. dz is minus gamma dm. And so I can rewrite my integral as integral with a minus sign now, and minus 1 over gamma, and then integral dz over z. And now we have to think about our limits of integration. So this lower limit is r minus gamma m0, and this is r minus gamma m of t, and this is integral from 0 to t of dt. So the right hand side is just t, and the left hand side, well, let's see. So I can rewrite this as minus 1 over gamma, and then log of z, r minus gamma m of t over r minus gamma m0, and that's equal to t. So I have log of r minus gamma m of t over r minus gamma m0, and that's equal to minus gamma t. We're almost done. So now I take the exponential of both sides, and I'm left with r minus gamma m of t is equal to r minus gamma m0 e to the minus gamma t. So finally, after a lot of work, we're left with m of t is equal to r over gamma, and then plus 1 over gamma, r minus gamma m0 e to the minus gamma of t. So that's our general solution to this problem. Let me just check. Let's check a few things to see if we're satisfied that this makes sense. So first of all, what is the long time limit? What happens when t goes to infinity? So t goes to infinity, m of infinity is equal to r over gamma, and I'm going to call this m star. So that's a steady state value of m of t. So in the long time limit, the number of mRNAs settles down to a value which is r over gamma, and that's pretty interesting and neat. You can see that the steady state value, the larger r is, the higher the steady state value will be. The larger gamma is, the smaller m star will be. So that seems to make sense. What about at t equals 0? So at t equals 0, this gives me, let's see, this seems to give me, I'm still not 100% confident, but let's just see what happens. M of 0 is equal to r over gamma plus r over gamma minus m0. And if I start out with none, let's set this equal to 0, then m0 will be equal to 2r over gamma. And so for this is a specific initial condition. Okay, there are many possible initial conditions, but I'm choosing the one in which the system starts out originally with no mRNAs. So you can think of this kind of as like being induction. Then in that case, m of t is equal to r over gamma, and then when I plug in this value right here, what I'm going to get is minus r over gamma e to the minus gamma t. So I have r over gamma 1 minus e to the minus gamma t. So that's the solution when I start out initially with none. Let me just show you that. So that's this red curve right here. So this is the solution. Maybe I can write it down. So this is m of t is equal to r over gamma 1 minus e to the minus gamma t. That's what this solution is. And we could look at other error cases as well. Again, let's just check this out. If t is equal to 0, then m of 0 is 0. If t goes to infinity, I get r over gamma, so this satisfies my sort of two limits that I was interested in. Let me also just comment on this idea of the steady state. So remember that our ODE, our differential equation, was dm by dt is equal to r minus gamma m. So this equation, the right-hand side, I can think about the right-hand side by looking at the relative magnitude of the two terms. So this guy is the R term, and it's constant. What I'm plotting on the x-axis is the number of mRNA molecules. I'm asking, what's the rate of production? The rate of production doesn't care how many mRNA molecules there are currently. So that's why it's the green curve, which is a constant. On the other hand, the degradation term, this piece, that's gamma m that I'm plotting, that does care. The more mRNAs I have, the higher the rate of degradation. And so these two curves, when green is above red, the system is moving to the right. The number of mRNA molecules will increase because this quantity is positive. On the other hand, over here, so over here I have r minus gamma m is less than 0, so the number of mRNA molecules goes down. What that tells me is that this is a fixed point. This point right here, which is m star, is the point at which the rate of growth and rate of degradation are exactly matched, and so the system doesn't change over time. And that's exactly what I'm showing you here. This asymptote right here, this is m star equals r over gamma. So that's what we're seeing there. I just have one last point to make, which is, interestingly, if we were in the classroom, I would ask everyone to guess, does the time scale, note there's a time scale here. The time scale I'm going to refer to, like this time scale somehow. The time, if you were to follow this slope until you hit saturation. So I'm going to call this t transient or something. In other words, this is the time it takes you to reach the asymptotic value. And if I were to ask people to guess in the classroom, it could be dependent only on r, it could be dependent only on gamma, or it could be dependent on both r and gamma. And most people think it depends on both r and gamma, but you can already see by looking at this equation that the only time scale in the problem, t transient, is equal to 1 over gamma. So 1 over gamma is the time scale that it takes to reach saturation. It does not matter what r is. Now you might say, well, that doesn't make any sense, and the point of that was just to show you here that even though these guys have different slopes, so this is r over gamma, and this is a different choice of r, okay, 2r. What you see is that in both cases, the time it takes to reach saturation is the same, which is shown right here. Why is that? Because even though in the red case it's got to go farther, it goes there faster. And so changing r does not lead to a different time scale for relaxation to the steady state value. So what have we done? We've basically done our first example of the rate equation protocol. We've used it to compute the average number of mRNAs. It led us through the entirety of identifying our field variables. We enumerated the possible kinetic steps. We wrote down a differential equation and we solved it. And so all those things were in play. It looks like one little discrepancy, which I'll leave to you as viewers to think about, is this minus sign. I think I got a plus sign down below, and so we'll have to sort that out. So that's it for our first experience of the rate equation protocol. Thanks.